Hello, my name is Dror Regev. Welcome to this session that start the design of RF CMOS PAs, power amplifiers. So power amplifiers are at the transmitter front end of transceivers, RFIC transceivers. So we can see the schematic of a PA really at the front end of the transmitters. Sometimes there is an external power amplifier where it's not necessary. In many technologies there is no external power amplifier. So when we talk about design considerations for a power amplifier, so the first thing comes to mind is the adequate power out of this amplifier. So it needs to be able to deliver a minimum amount of power to the load. It has to be efficient because this is usually the circuit that draws the highest currents in the RFIC, and it will really affect the efficiency of the total RFIC. Especially if it's a high power out amplifier, efficiency becomes more and more important. And the efficiency is even magnified by the fact that modern modulations are amplitude modulations, and most of the time the power amplifier draws current but really amplifies lower signals and not really transmitting full power out. So the efficiency really becomes critical when we design modern power amplifiers. Linearity is another important design consideration when we talk about especially amplitude modulations. Of course, we need to have a lot of gains, otherwise the stage before the power amplifier will also have to deliver high power. So we want maximum gain from this amplifier in order for the preceding stage to handle lower powers. It has to be stable. As we discussed before, every circuit has to be stable unless it's really generating frequency or it's an oscillator. But for amplifiers we have to ensure stability. So this is electrical stability, but also thermal stability and thermal consideration. Power dissipation is an important design consideration we need to take into account when we engage in such designs. Robustness to the load, the output load, and size are two more parameters that we will consider when we design an amplifier, power amplifier. We will go over most of these design considerations in the next slides, in the next sessions, but I just wanted to start with these design considerations before we really engage into design, so we will have the full picture before us. Class A PAs or linear PAs usually employ the common source topology that we met when we talked about LNAs. So the simplest way to start understanding how we design a power amplifier will be to take a common source transistor with an infinite RF choke or infinite inductor connected to the VDD, to the supply, DC block or ideal DC block, let's say infinite capacitor and resistor load. We will later on get rid of these ideal components, but for beginning the discussion it's easier to explain the operation with these. So the VDD will really appear at the drain when there's no signal at the input. Fast current switches cannot happen with ideal choke, so all the currents will need to come from the load. Of course, the ideal DC block will transfer these current transitions perfectly. and we can start understanding the performance or the behavior of this circuit from the quiescent bias point. So we have, this is the ID-VD curves of the transistor. We have a VDD that is present at the drain at a quiescent state. We have some quiescent current that we provide to the transistor to keep it in the saturation region. And we are introducing changing or alternating gate voltage as the input. IDS, the drain source current, will be the IDS DC and IDS AC that is introduced by the input VGS, and it will be IDS DC plus GM VGS, which is very simple to show, like we did in previous sessions. If we just want to check it, we can look at the ID-VD curves and see that when we increase VGS on this on these graphs, the drain current, drain source current, needs to be increased, and this is GM is just the coefficient that multiplies the VGS. When we talk about V drain source, so we also have the V drain source at DC plus an AC component. And this AC component is, in this case, comes in a negative sign because the current really comes from the load. The alternating current comes from the load, and if we use Kirchhoff laws, we find that basically when VGS increases, the voltage drain source really reduces. So it has antiphase to the current here. And we can see it here. We have the phase of the current and antiphase to the voltage drain source phase. And the load voltage would be equal to VDS, because it's really, if we consider the capacitor as a perfect short at AC, it's really the same voltage. And it will be, if we only look at the AC part of it, it will be minus VGS GM multiplied by the load RL. IL, this is the alternating current, will be also minus GM VGS, and we will use these load, current, and voltages in the next slides. So RL, the load resistance, will be the drain source voltage divided by IL, the load current, and it's going to be minus VDS over IDS. This sign is important because we use it to describe the load line on the ID-VD graph. The power that will be developed on the source RL will be IL divided by square root of 2 to get the RMS current, multiplied by VL divided by square root of 2, and it's actually I load times V load over 2, which from previous slide we can describe as GM squared times V squared times RL divided by 2. When we see this equation, we can understand that if one wants to increase the load on the power on the load, can either increase the input power, which is not a very smart thing to do because you'll need to amplify in a previous stage, but can also increase the GM. And also we can start to understand that GM must be constant, otherwise we get linearity degradation, as we will see later on. RL, yeah, it looks like if we increase RL we will increase P load, but there are limitations on RL, as we will see in the next slides. So it will not be a very good idea to just increase RL, because it will be shown that this is going to create nonlinearity issues. Load resistance, as we saw in the previous slide, was an important parameter determining the output power. However, we need to understand the effect of this load resistance on the operation of the power amplifier. So we are looking for an optimum, assuming there is an optimum. And in order to find this optimum, we start with two extreme cases. One is the case where the load resistance is low compared to that optimum that we are looking for. And what we find is, if we have a low resistance, the slope is such that we get current clipping. So here on this side we can see the current, and at certain amplitudes, if we want to increase the current, the output current, then we get current clipping, and this of course translates to linearity degradation, and we would like to avoid such cases. So we understand that the load cannot be as low as we want, but we need to find a better way to find this optimal load. The second extreme case that we will look at when we want to find this optimum RL is very high resistance, which is very tempting, because we saw when we started talking about output power of the power amplifier that really RL is with linear proportion to the power. So one can choose a very high resistance to increase the power. But what happens if we do that? Then we can see that the slope here is such that we get voltage clipping on this side. So here is the voltage swing, and at that VDS, the transistor is no longer in saturation, and so we get voltage clipping and degrade linearity again, and of course we would like to avoid it. So we know that we cannot take RL to the extremes, and we need to find this optimum we were after from the beginning. So if we want to talk about optimal load and maximum power, we need to find a load such that current clipping nor voltage clipping will occur. And when it occurs, it needs to be rather symmetrical. So it will be on both ends of current or voltage rather than on one end only, because one end really generates even harmonics, which are closer and harder to filter later on, where if we just square the circuit, the signal, so we will have odd harmonics like third, fifth, which are much farther and easier to filter. Any case, we know that it cannot be very low resistance nor very high resistance, and what we can describe is that we have a minimum voltage that we don't want to go under, and we have a minimum current that we don't want to go below. And if we just take this triangle that we get here and divide the voltage range, the allowed voltage range, by the allowed current range, we can find the optimal resistance. So VDSQ is the quiescent voltage, and V minimum will be the naive voltage. IDSQ is the quiescent current, and I minimum is the current where the transistor is no longer in saturation. Now the maximum linear output power will be the product of the maximum voltage swing divided by square root of 2 for RMS value multiplied by the maximum current swing RMS, and we can find very easily that this is the voltage range multiplied by the current range over 2, which is the maximum linear power one can get from a specific transistor with a specific current bias. We have just discussed and described the optimal load resistance. However, we have neglected the output resistance of the transistor so far. We have assumed that I drained source current is really being sent to the load or being drawn from the load, but there is some internal output resistance we have neglected. Now we want to discuss it, and really this output resistance is in parallel to the load resistance. So what we can do to simplify the treatment is to understand that the actual load will be these two resistances in parallel. However, we lose some efficiency here because the output resistance does draw some current which is being wasted internally in the transistor. But calculation of the load line will be to find the optimal load, and then understand that this load will be both R load and R drain source in parallel. And of course, if our drain source will be high enough, most of the current will be actually delivered to the load, and we don't waste too much of the output current. Another confusing design consideration for many RF engineers or microwave engineers is maximum output power delivered to the load versus output matching. Because as we discussed when we matched the LNA input, conjugate matching really takes care of the output of the circuit being matched to the load. And with this classical impedance matching, we need to make sure that the real value of the output transistor and the real value of the load are identical, where the imaginary parts are identical in the amplitude but negative in sign. So one side would be capacitive, for example, the other one will need to be inductive, and this is the imaginary matching, or the impedance matching of the output. However, we just described the maximum power to be delivered to the load in the case where RL is much higher than RDS. So this is really the difference that people need to understand when they're going to design a PA. We cannot achieve simultaneous match like we did with the LNA for both maximum output power and minimum reflections at the output. And usually the trade-off will be such that most designers will really prefer to deliver as much power to the load rather than match the output as conjugate match, just because of the efficiency issues that are becoming so much more critical these days when most of the devices really rely on a battery rather than a power supply that is connected to the outlet. So this distinction must be remembered when we finish the design, because especially when you want to specify to somebody else, you specify the output power, then you say, oh, but it needs to be matched. You cannot get both simultaneously, and this needs to be clear. We have mentioned efficiency, and this slide defines efficiency. There are a couple of ways to define efficiency. We'll just go over two of them. So first efficiency measure that we will describe here is drain efficiency. And basically what we do is we take the power delivered to the load, and just divided by the power dissipated on the drain. So this would be the DC power dissipated in the circuit. So it would be the DC voltage multiplied by the DC current. The other way to look at it is power added efficiency, where we can see here, in this case we say, okay, we have generated some AC power on the load, and we need to normalize it to the DC power that was invested in the transistor, but we have also invested some AC power at the input, and let's just subtract it, because this is another power that we invested in the circuit. So this is power added efficiency. It's just a different way to look at the same power amplifier, and just a matter of, different companies, different school of thoughts, which way of definition they want to choose. And of course there are other definitions, but the idea is that we really want to see how much AC power was delivered to the load compared to how much power we invested or dissipated in the circuit. Thank you for joining me on this session about Class A power amplifiers. Hope you enjoyed it, and hope you will join us for the next sessions or visit our website.